Hello everyone. It is a pleasure to participate in this renowned symposium in 2022 and share part of our research in electronic interface applied in CMOS. My name is Zi Chen. I am an undergraduate student at the University of British Columbia.
I am Gabriel, a PhD candidate from the University of British Columbia, and we are going to present a unique and systematic method to produce an optimized impedance matching network for poly-CMOS. CMOS is an emerging alternative to piezoelectric transducers. Their operating principle relies on arrays of thin vibrating membranes electrically actuated by capacitively induced forces. Most popular membranes are fabricated with silicon-based material, like silicon nitride and polysilicon. This work is based on CMOS developed in our group, the poly-CMOS. The distinction is the placement of the top electrode between two layers of polymer, SU-H, which results in several advantages in terms of design and performance. Poly-CMOS offer a better acoustic matching to the propagation media due to its lower acoustic impedance compared to silicon-based CMOS and piezo transducers. For example, the human tissue and the CFRP plates have 1.5 and 3.7 megarails respectively, while poly-CMOS has 3.5 megarails, about 8 times lower than the 30 megarails in piezo. This means poly-CMOS has a broader fraction bandwidth, allowing improved axial image resolution and, by consequence, better images. However, due to its limited effective membrane and deflection areas, CMOS outputs lower power. Fortunately, impedance matching improves power transfer efficiency, but normally this will reduce bandwidth and, by consequence, heavily affects the image quality. First of all, let's see what is impedance matching. For the sake of simplicity, let signal amplitude be the power level. An incident wave is sent by the transducer in the form of a mechanical wave. Because of the impedance mismatch between the medium and the CMOS, not all available power are transmitted. The same happens in the electrical domain, where not all of the electrical power generated by the source are translated into mechanical power. Ideally, with the presence of electrical and mechanical matching, power received by the medium should be the same as power generated by the source with no distortion to the signal shape. However, normal impedance schemes are not perfect. It allows good matching at some frequencies better than in others. This means the signal is only partially transmitted. This leads to lower power and distorted signal. Let's see why this is happening. In our case, we will be focusing on electrical matching only. To understand why, first we need to introduce the small signal model of the CMOS, shown in figure A. During normal submersed operation, the CMOS has very low quality factor. The quality factor is low enough such that there is no resonance effect. We can take advantage of this property and simplify the small signal in A to B when the frequency of concern is in the shaded area. The simplified circuit consists only of the intrinsic capacitance of the CMOS and the mechanical and acoustic load. From now, we can analyze a simple impedance matching network between source, normally a pulsar, and the CMOS. In the top figure, there is no impedance matching. We see that the power delivered is low. The graph at the right side shows that only a fraction of power is dissipated by the load. On the bottom figure, the simplest form of impedance matching for our poly-CMOS is the pi matching network. A simpler matching technique is a two-element L matching, but it will not work in this case because C0 is too large and cannot be changed. Looking at the bottom graph, we can see a perfect power transfer only at 5.5 MHz. This behavior happens in narrow bandwidth impedance matching. This simple matching circuit restricts the passband frequency, thus distort the signal shape, oscillation, and ringing.
To combat this issue, we developed frameworks for wideband impedance matching. Figure A is a typical single-period 5.5 MHz bipolar pulse used to excite an ultrasound transducer. Figure B is the spectrum density of this pulse. We see that this pulse covers a wide spectrum ranging from 0 to 10 MHz. Simple impedance matching only covers a narrow frequency spectrum. which cause ringing in the received signal shown in Figure C. This ringing is not a concern in applications where signal reception is not critical. For ultrasound imaging, this ringing will cause undesired artifacts in the image. With our matching, we see a greater peak amplitude and less ringing, just because it is a wideband matching and it covers a wider spectrum. When we look at the frequency spectrum of different matching schemes, there is a difference in maximum power delivered at a single frequency between simple matching in orange and our matching in blue. However, because we are covering a wider spectrum, we get better response in a single amplitude and shorter ringing time, resulting in sharper image. Going back to Figure A, we see the trade-off between maximum transmitted power and bandwidth. However, is it possible to have a wider bandwidth and higher power at the same time? Turns out, there is a trade-off between maximum amplitude and bandwidth. This trade-off is described by Fenelberg criterion. This criterion is a mathematical proof that limits the total area under the power transfer curve for a given load configuration. Our synthesis uses filter design methods to closely approximate the bandpass shape desired. We use iterative method to tune filter power response to fit the Fenelberg criterion. The red curve is an ideal breakwall filter response, and we can see that after many iterations, the passband shape closely relates to the shape of a breakwall filter. This makes sure that the designed passband shape is actually realizable. The transfer function is then synthesized using Calvert Form 1. With this technique, we can produce matching that closely related to the bandwidth and power level of an ideal breakwall filter response. The red curve in A and B are response of ideal breakwall filter that satisfy the Fenelberg criterion. Wideband IM1 and wideband IM2 are matching networks synthesized using our method. They lie closely to the curve of the ideal breakwall filter. To the left is our experimental setup. This is the CMOT. It is submerged in a bath of IPA, which have similar acoustic properties than water. The impedance matching circuit is constructed on a breadboard. The parasitic of the breadboard and wires are verified and considered using an impedance analyzer. The block diagram for the circuit tested and their simulated frequency response are shown to the right. Here are results of our experiment. In the time domain signal, we see our wideband matching delivers higher peak amplitude without much ringing. In the power spectrum density, simple impedance matching delivers higher power at a single frequency, while wideband matching delivers more overall power. These experimental measurements validate our theoretical and simulation result. With our matching, we have better control over the shape of the passband compared to simple matching techniques. This is because that we define our passband shape using filter polynomial approximation. The power to bandwidth trade-off is optimized using theoretical limits to ensure efficient use of the area under the Fresnel integral. Our design allows any power to bandwidth trade-off independent of order of the filter. More components only produce a more ideal response. This type of matching approach also applies in the acoustic domain, and this is something we are currently working on. For the particular circuit we tested in our experiment, we achieved a 5 dB increase in power and a reduction of 30% in bandwidth. However, one of the drawbacks is that we cannot produce perfect matching solution when parallel capacitance is too high. Since we are not targeting for a perfect matching, this turns out not to be an issue. Also, the quality of the matching is affected by the component's tolerance errors. This dependency is under investigation by our group. Overall, this structured optimization algorithm demonstrates the ability to greatly improve the acoustic power of CMOT with a reasonable compromise to its intrinsic wider bandwidth. Now, we extend our greatest appreciation for support from the National Science and Engineering Research Council of Canada, the Department of Electrical and Computer Engineering at the University of British Columbia, and the Federal Institute of Education, Science and Technology of the Amazon. Special thanks to IEEE International Ultrasonic Symposium for hosting this event. Thank you.